The parallel plate capacitor is a very important object that we are going to return to multiple times this semester. Initially, it's going to be something that creates a uniform electric field, so we'll be placing lots of things in it as a way of having things interact in a uniform electric field. We're also going to eventually make capacitors within circuits. So this is something that's fairly interesting in that right now we can meet it in a very ideal, simple manner, but later we're going to see it really occurring in the real world, right? There are capacitors in your cell phone. So what is a capacitor? And note that technically this is a parallel plate capacitor. There are capacitors of other forms, but for a very long time, we're only going to be talking about parallel plate capacitors, so I'll just shorten to calling it a capacitor. So the basic structure is that there's two electrodes, and these are just conducting planes, so big sheets of metal, for instance, and they are charged. Note that they are equal in magnitude, but opposite in sign. So one is positive Q, one is negative Q. They are separated some distance d, and they each have an area A. So this is the basic structure. So this in itself, once you see something that looks like that, you can treat it as a parallel plate capacitor. Now, sometimes we're going to have these plates be infinite in size. Sometimes they're going to be square. None of that matters. Once you have two plates, equal in charge but opposite in sign, separated by some distance, you have a parallel plate capacitor. Note that they are in fact parallel, right? These two in this case, discs are kind of like an Oreo sandwich where they do align. So that's also fairly important. And the fact that they're the same area is also important. We could start to do calculations asking what happens if they're different areas, but we don't want to think about that for quite some time. So the first thing we need to think about here is what the electric field is actually around and inside this capacitor. Now I'm going to take a slightly different approach than the book does in that I'm going to tell you the answer and then I'm going to justify it. This is a place where I see students get stuck. And in many cases, you read through it, you think this is pretty simple, and then later you can't necessarily figure it out again. So let's first introduce the answer and let's see if this makes sense to you. First, we have two regions to worry about, inside the parallel plate capacitor and outside. And that just means inside being between the two sheets, outside being on the outside of those two sheets. So inside is the cream filling of the Oreo. The field is Q over epsilon A. Now, one thing that Q over A should remind you of is eta, surface charge density. So Q over A is eta, and the other form here that you should notice is that this is just like the electric field from a plane, which was eta over 2 epsilon naught. So this is Q over epsilon naught A, or eta over epsilon naught, which is just like a plane, except there's a factor of 2 difference, and that's going to be really important. Now, this is uniform. It doesn't matter how close you are to each of these planes. Then, on the outside of the capacitor, it's 0. 0 close, 0 far, absolutely 0. So the argument we're going to make to get here, and we're going to do this visually, is that we can treat each of these as an infinite plane, where the electric field was given by eta over 2 epsilon naught. Now, because these each have the same area and the same charge Q, they each have the same eta, but one is positive, one is negative. So they each have the same eta over 2 epsilon naught, but on the outside, the directions of the field cancel, and on the inside they add. So that's why this factor of 2 has gone away, because 1/2 plus 1/2 equals 1. So that's the basic idea. Inside it's uniform, given by this equation. On the outside it's 0. So let's look at why that is. What we're going to be showing here are the electric field directions from the positive electrode and then from the negative electrode. So when you see a subscript negative, that means from negative. Subscript positive means from positive. So first, let's look at the positive ones. Now we know that the electric field from an infinite positively charged plane points away from it. So on the inside, that would be to the right. On the outside, that would be to the left. So hopefully that makes sense. So initially, just focus on this. We're looking at one component of the electric field. But then we take my minus and we look here and we look there. So for a negative infinite plane, it points towards it. So on the right, you have it towards, and on the inside, you have it to the right. So on the inside, they are both pointing to the right. They are both pointing from away from the positive or towards the negative, so that means they add. But now notice that I didn't actually show you the last, there's actually 3 from each of these. This one also creates an electric field over here. When you add fields, remember that the fields go through all space and that then we just add them. This positive plane of charge does not, remember this is an edge view, does not in any way block the field. Now, there's going to be some situations later that we talk about fields inside conductors, but a fundamental thing is that this is not blocking the field. Now, this is creating its own field, so we do need to add them up. But if all we're doing is looking at the field from the negative, not only do you have it on the right and on the left, but you also have it slightly further away. That's just like saying over here, we also have a field slightly farther away. That's true. So this also creates a field component over there. And similarly, this one also creates a field over here, right? Each of these creates a field at every point in space. So when you look on the outside, these 2 fields cancel because the one from the negative electrode points towards the negative electrode. The one from the positive electrode points away from the positive electrode. Those are 2 different directions here. They're equal in magnitude because the distance does not matter. And the same pattern holds over here. So it's really important that when we say that the net electric field is equal to 0 on the outside, it is incorrect to say because one electrode blocks the field of the other. That's an unphysical way to talk about it. Again, if you're thinking about it that way, that's wrong. That's a simplification that is just flat out wrong. But the superposition gives you equal and opposite fields, which sums to 0. On the inside, they're equal in magnitude and in direction, so they sum. So that's how we get there. And again, the value here would be eta over 2 epsilon naught for each of them. So you're left then with eta over epsilon naught on the inside by multiplying by 2. So one thing to think about is that we treated these as if they were infinite planes, which gave us a uniform field everywhere inside. Not only did it not matter how close you were to each electrode, the field did not change, but it also didn't matter how far you were up or down. Now this is an ideal capacitor. This is our nice physics class, easy to calculate capacitor. A real capacitor actually has edges. Once you have edges, that means that near the edges, the fields start escaping outwards. That actually means that you do have a little bit of electric field on the outside, and you can think of this as effectively continuing some of these field lines all the way around. That's all that's happening here. So that's a real capacitor, but this is kind of a nightmare to calculate. So in order to not calculate this, we are instead going to always treat them as ideal. So again, even if we do talk about a finite size, we'll still use the infinite plane approximation. So part of the value of this, at least right now, is that it creates inside of it a uniform electric field. There are many reasons why we will want to talk about uniform electric fields, mostly because they're simple. So when we talk about the motion of a charge or the motion of a dipole in an electric field, it's going to be really hard to do that if it's a changing electric field. And keep in mind that an electric field from, for instance, a point charge decreases with 1 over r squared. So that is certainly changing. So whenever you see an electric field that looks like this, note that all of the vectors point in the same direction and all of the vectors have the same magnitude. That tells you that this is a uniform electric field. Now in many cases we're just going to directly work with this, but if you want to know, well, where is this electric field coming from? The answer is like a really big parallel plate capacitor outside the page that you can't really see. So we'd have some positives over here, and then we have some negatives over here. So frequently we will only work with the electric field, but you can infer that this is within a giant parallel plate capacitor.